Hello everyone. Okay, so we are entering chapter 4 in this video. We're discussing chapter 4. And this chapter covers three main things, which is all going to be work done, and then we're going to talk about energy and power, and then the conservation laws that is related to it. Okay, so let's begin by defining what is work done. So say you have an object, and that object travels at some displacement, right? And then to make that happen, we have applied some force. Okay, so what is work done? Well, work done is simply the scalar product, right? Scalar product, dot product between the force that causes the motion, or the force applied to that object, and the displacement of the object. So we can see that because it is a dot product, we have two vectors, because they're interacting, via dot product, we will have here the work done to be scalar. Scalar meaning the only important thing about it is its amplitude. Okay, but it's particularly important for us to talk about the direction of the vectors that is involved. That means you will have very different values if the force is in the opposite direction. So one major important thing here is that it's very important for you to realize, okay, it's very important for you to realize that the direction is really important. Okay, so just to mention something, the unit here, the units, it's quite easy to see. I have Newton for force, and then I have meters for displacement. So the unit is simply going to be Newton meter. Okay. Now let me just give you a comparison. Say you have an object traveling in this direction, then its force is also traveling in that direction. The angle between them, so F dot S. So if I have cross product, if I have dot product, it's just simply going to be cosine theta, theta being the angle between force and displacement, right? So then my theta is simply going to be 0, and then my cos theta is simply going to be 1. Therefore, my work done is just the magnitude of F multiply with the magnitude of S. Okay, now this is going to be very different if the body is traveling to the right, right? But the force applied is in the opposite direction. Okay, this is just for me to mention. Okay, my force and my displacement will have an angle of, say, see the angle here, let me just find it out. The angle between them is going to be 180, okay, and that's going to introduce a negative sign. So negative magnitude of F times magnitude of S. Okay, so it's particularly important for you to know that this theta, when you expand F dot S, when you expand this, you have S, the magnitude of F, the magnitude of S, and then cos theta. It's very important for you to realize that this theta is the angle between F and S. So if they're in the same direction, you'll have 0 degrees. Then I'll have just cos 0, which is 1. Okay, so that's just positive. Whereas if I have them in the opposite direction, so 180 degrees apart, I will have a negative sign there. So a negative sign there. Okay, so that covers the work done part of this video. Next, we'll be talking about energies. Okay, so now the second part of this video is going to talk about energies. There are, let's see, let me check again. Confirm that there are three types of energy that you need to consider. Okay, three types of energy. The first one, which you should be familiar with all of them, but let me just mention the first one should be gravitational potential. So gravitational potential energy, and this is simply So I'm going to label it as EGP. This is simply going to be mgh. Now m is just the mass of the object, so that is just the matter content of the object. G is the gravitational acceleration. If it's on Earth, we will use G. If it's not, we'll use some other values. And then we have h, which is how far that thing is from the surface of the Earth. So it's height. So if you have if you're doing an experiment where it's all done in on Earth, right? On Earth, the two main things that are going to affect it is mass and height. Okay, the higher you go, the more potential energy, gravitational potential energy that you have. That's all it is. Okay, so it's particularly important. Now again, the unit for energy here, I can deduce it. Now I have mass to be kg, G to be ms negative 2, H is just m. Okay, if we were to compare again with, so this is in SI unit, right? SI unit. But we can also simplify this to be, so kg, meters per second. This is just Newton, then I have Newton meters. Okay. Another alternative unit for this is what we call joule. So joule is just Newton meters. Okay. Okay, now moving on, the second type of energy that we want to talk about is the elastic potential energy. Okay, this is a consequence of Hooke's law, right? We have U equals to half kx square. Now they both have the word potential in it, right? It's simply because when we talk about potential energy, it has a tendency to do something else. So for example, if we move an object quite high from the earth, it has a tendency to fall down. Same thing with the elastic potential energy. If I have an extension or compression on a spring, well, on an object attached to a string, it has a tendency to push back, right? So for gravitational, the main factor is the height, and then for elastic potential energy, the main factor is what we call the spring constant. Okay, again, they will still have the same energy, sorry, the same unit. So in SI unit, you will have either kg m square s negative 2 or Newton meters or joules. Okay, you can have all of that. All right, so this is the energy related to elasticity. If you pull something elastic, it has a tendency to either pull back or push forward. Okay, so its energy is stored in the elasticity of the material. Last but not least, we have kinetic energy. Sorry, it should be number 3, right? Last but not least, we have kinetic energy. The first two, the gravitational and the elastic potential energy, are about the potential for the object to do something, whereas the kinetic energy is the energy related to moving objects. So the object must be moving to have kinetic energy. It has to have some velocity. Its velocity cannot be zero. And this is calculated quite simply, half mv square. Again, mass of the object. Okay, its units, right? It's SI units. It's going to be the same as before, which is kg m square s negative 2, and then or joule or Newton meter. Okay, so that's just to introduce the 3 types of energy that we would consider. Okay, I'll just summarize it here fairly quickly. Okay. The first one being gravitational potential energy, where I have mgh, and then the second one will be elastic potential energy, where I have half kx square, and then the last but not least, I have kinetic energy. It is half mv square. Okay, and they all have the same units because they're all energies. All right. Okay, the next part of this video, I'm going to talk about the work energy theorem. Okay, this is the third part of this video, and I'm going to show relatively quickly on how you can derive out the work energy theorem. Okay, so let's begin by consider the equation for work done. Work done is simply F dot S. Okay, assume that the angle between them is 0. What I'll have is just F times S. Here I'll have the magnitude of F to be F. I'll just change the symbol, and then the magnitude of S to be, well, just S. Okay, so that just makes my life easier. Okay, so if I were to start with that, right, I can apply Newton's second law, right? F equals to ma onto that. What I'll have is going to be ma times S, right? And then I want to look at the velocities, so I consider a velocity equation. I have v squared equals to u squared plus 2as. I can rearrange that such that I'll have a equals to v squared minus u squared over 2s. So then I'll have m times s times v squared minus u squared over 2s. As you can see, the s's just cancels out, and I can write this quite nicely to be half m v square minus u square. I can multiply this into the brackets. What I'm left with is half mv square minus half mu square. Okay, and if you remember from the last part of this video, half mv square is just the kinetic energies. So it is going to be the final kinetic energy minus the initial kinetic energies, right? So work done is simply the change in kinetic energy. This is the work energy theorem. The work energy theorem says that work done is simply equal to the change in kinetic energy. Why does that happen? Well, let's think about it. You have a ball moving, you hit it, right, such that it changes direction, or it slows down, or it makes it faster. It depends on where you hit it, right? If it's moving to the right and then you push it to the right, it's going to increase in velocity. Okay, so that force that you did, that push that you did, is the work done you do onto the object. Okay, so if v is bigger than u, then this is going to be work done onto the object. So again, work done onto the object. Okay, so it's relatively important for us to mention something else. Imagine if you have a ball and then you push it, whilst it's moving, you push it to the right and then you push it to the left. Now, if you think about it, you will have to consider the net force. So your net work done is going to be equal to the net force times displacement. All right, so it's very important for you to consider all of the forces. Okay, unless if it's asking the work done by some other force. So let's say it's the work done by the gravitational force, then you will have to consider only gravitational force times displacement. If it's asking for probably work done by potential energy, so elasticity, or a spring, right? A spring, then you'll have to consider only the Hooke's law, so Hooke's law times S. It depends on what is the force. But if it's asking for net work done, you will have to figure out what is the net force on the object. Okay, so that's particularly important. Now, that is all on work energy theorem. In the next part, I'll be talking about conservation of energy. Okay, we're at the fourth part of this video. This part of the video is talking about conservation of energy. Specifically, the conservation of mechanical energy. When we talk about mechanical energy, it involves the the three energies we've mentioned before, which is going to be our gravitational potential, we have our elastic potential, and we have our kinetic energies. So energy is always conserved. That's what conservation of energy means, right? That's what the statement of conservation of energy. The statement is simply that if you add up all of the energies, right, before and after, so final minus the summation of all of the energies initial, it must be conserved, must be conserved. Okay, so what this means is that initially we might have UGP initial plus UEP initial, then plus our kinetic energy initial, right? And then we might have our UGP final plus UEP final plus our kinetic energy final. This is our general equation that we can apply in most cases, in most questions, and then we just need to figure out which one has zero, which one ends up being zero. So if it doesn't have a spring, then EEP is going to be zero. If there's no height at the final stage, you might not have any EGP, probably. It depends on the situation, right? So it really depends on the question, which we will do some examples of in the class later on. Okay, now I might as well add a second part for this, which is going to be power. Power is simply the rate of change, or rate of change of work done. Okay, so power is defined by the rate of change of work done. That's what it means. Now, one of the crux about it is that, okay, I can assume these changes are going to be very small. I'll have delta W over delta T. This is what we call, if I make that assumption, this is what we call the average power, because it has 2 points. I have the initial work, final work minus the initial work over final time minus initial time. So P average is equals to this. P average is equals to delta W over delta T. Now, for instantaneous power, let's call it instantaneous. This is average. These are the two types of power that you need to work out. Okay, so for instantaneous power, what we do instead is we are going to use, okay, we look at work done, and then we know that it is going to be equal to Fs, right? See, if you have constant force, you can take out the value of F. I'll have then, okay, F times ds over dt, which is just the velocity. Okay, which is just the velocity, and power, the SI unit is going to be in watt. Okay, so there are two different types of calculation for power. The first one being the average power, the second one being the instantaneous power. So it depends on the information given in your question, right? If they give you velocity, so for example, determine the power when the object has a velocity of 5 meters per second, then it's actually asking about instantaneous, right? Instantaneous power. Okay, so it's very important for you to be able to read the question and deduce which type of power is it asking for. Okay, all right, so that is the end of this video. All right, there's no new parts after this. The next video is going to be on chapter 5. Okay, thank you very much.